and CEO of ScaleOut Software, and I'm very excited to talk to you today about how digital twin models can be used for stream processing. So I hope this is what you wanted to hear about. If you have any questions, please send those questions via chat to David Brinker, who's our host, and David will collect those questions and then read them out at the end. We'll see how much time we have questions for. This webinar should run about an hour. We'll try to make it into slightly before the hour, so there's a few minutes for questions. This is talking about a software technology, so in case that was confusing, sometimes people get confused. We're talking about ScaleOut software and our technologies for in-memory data grids and computing, which are software technologies. We're going to talk a little bit about some of the challenges for stream processing today with an example in e-commerce, and then talk about how the digital twin model addresses these challenges in a very elegant and powerful way. And we'll look at how digital twins can be run using in-memory data grids, again, software technology running on a cluster of commodity servers or in the cloud, and some of the advantages of this approach. And then we'll compare that to the traditional approach and show you how you can get much deeper introspection on incoming events in stream processing applications. We'll have two code examples, so there is some code in this webinar, a C# example that makes use of our Digital Twin Builder software toolkit, and then another example in Java which shows you how you can incorporate data parallel feedback in real time to a stream processing application. So first, we'll talk a little bit about ScaleOut software, and go to this slide here, and I think I will bring up the a little arrow so that I can point to things. There we go. So ScaleOut software develops in-memory data grids, which are software middleware that run between an application and the operating system across a cluster of servers, whether they're virtualized servers or physical servers, either hosted on-premises or in the cloud. And this technology can be used to store fast-changing live data in real time for scaling application performance by offloading databases, and also for introspecting on this fast-changing data for operational intelligence so that more effective feedback can be provided to live systems. And so this technology combines both in-memory data storage and computing, and we'll see in the next few slides how it does that. And then we'll see how you can apply this technology to building digital twin models for stream processing. We've been in the market since 2005 with 450 or more customers and running on more than 10,000 servers. Here is a sampling of some of our key customers, just for your interest. And now we'll talk just one more slide about our products and then talk strictly about technology moving forward after that. So we have two classes of products. First of all, our products for in-memory data storage, and that's our ScaleOut State Server product with its companion ScaleOut GeoServer. And this product is primarily targeted at storing live, fast-changing data within in-memory data grids that span a cluster of servers. And it provides APIs in Java, C#, C++, and C. It can be deployed on-prem or in public clouds. We're in the AWS Marketplace and also in Azure. GeoServer expands this technology to run across multiple physical locations for disaster recovery and for global data access. Now, in-memory computing products comprise ScaleOut Stream Server and the ScaleOut Digital Twin Builder Toolkit, which goes with ScaleOut Stream Server. And this allows developers to build stream processing applications using the digital twin model, using both Java, C# and soon to be released is JavaScript support. It also has APIs for very fast event posting using ReactiveX and connections to Kafka, Azure IoT, and coming soon is connections to AWS IoT. In addition, you can perform real-time data parallel analytics such as MapReduce on data stored in the grid so that you can combine both stream processing and data parallel analytics. And this ability to combine those two capabilities, stream processing with low latency and real-time data parallel analytics, is the hallmark of this technology and also what makes it of interest for improving the quality of stream processing as we move forward. So let's first of all take a little bit closer look at these core technologies of in-memory data grids and in-memory computing. So I'm not sure. Normally, if I could have you raise your hands, I'd find out who knows what an in-memory data grid is, but WebEx doesn't let you do that. So I will just give you a quick primer on in-memory data grids. So again, it's a software technology that runs on a cluster of commodity servers that has a logical view for applications. Remember, this is middleware software. So there's a logical view, and then there's a physical implementation of the in-memory data grid. So the logical view is collections of objects stored using key value pairs within the grid. So objects are separated by type generally into different collections and stored in the grid, and they're accessible in a location transparent manner by multiple clients accessing the grid using simple create, read, update, delete APIs in multiple languages. With, in addition, parallel query. An in-memory data grid should not be confused with an in-memory database with SQL APIs. Instead, it's NoSQL view of data using key value pairs. And it allows applications that have business logic state or stream processing state to store data in an object-oriented manner very simply in the grid with low latency, fast access, and scalable throughput. So that's the benefit of an in-memory data grid. It's storing fast-changing data in memory, and we'll show you a little bit more about how it does that in the next slide. So in-memory computing adds value to that by allowing this stored data to be analyzed in real time, either through stream processing or through data parallel operations. And by storing the data in a cluster of servers and then performing in-memory computing operations on that data in place, you avoid network bottlenecks because data does not have to be moved out of the grid to perform computing operations. And that's a key benefit of in-memory data grids, is that they have transparent scalability, scalable throughput without bottlenecks because data motion is minimized. In addition, most in-memory data grids, such as those that we make, have integrated high availability using techniques of data replication, so that if one grid server should go down, this represents a grid server and this represents another one, the data is not lost because there's a replica of every stored object on some other grid server. So this ability to have under-the-floor transparent high availability along with scalable throughput and location transparent access makes an in-memory data grid extremely easy to use and very powerful for both storing, retrieving, and analyzing live data. Now let's just look under the hood a little bit more to see how this technology works. You may ask, why are we doing this since you're here to hear a talk on digital twins? It's because this technology is what enables digital twins to do their job efficiently in a highly scalable manner. So we want to have an underpinning of what the technology is doing, and then we'll look at how digital twins make use of this technology. So how do we integrate computation into an in-memory data grid? Well, first of all, in-memory data grids are implemented typically as service processes or daemons in Linux or service process in Windows, that one process per server. So this represents 3 servers, which could be physical or virtual, with a grid service process running on each one. And then on each server, or host we call it here, we spawn a second process called an invocation grid worker, or IG worker here. And this runs a language runtime, either a JVM in Java or a .NET runtime or a C runtime if it's C or C++. And so, or it could be Node as well. So these IG workers then allow us to execute user code which is shipped to these workers transparently by our APIs, so that when this code has been positioned on all of the IG workers, then now we can send requests to these IG worker processes and they can access local data. So what we're doing with this invocation grid, so-called invocation grid, the set of IG worker processes, is we're avoiding network transfers to access data for processing. So the key to the scalability of an in-memory data grid for in-memory computing is hosting the code on each server in the grid in an IG worker process and having it access only local data. So this avoids network bottlenecks and allows us to take full advantage of the object-oriented model. And it's also leveraging all of the cores and on one server, on each server, and also all of the servers in the grid, so you get very nice transparent scalability. So that's how this is done. Now, for stream processing, what we will do is we will execute event handlers for each incoming event. So we might have many clients, say Azure IoT Hub and AWS, and they're streaming events into the grid, and these events can then be directed to hosts within the grid, typically by associating these events with objects in the grid. And as we'll see later, these objects are digital twin state objects. But that's not necessary. They can just be associated with random objects if you prefer. In any case, the methods are then shipped out to the grid workers and then run within the grid workers, only accessing local data for on the grid service on that server. So by doing this, we can execute event handlers with extremely low latency, and these event handlers can access associated context or state information with low latency and high scalability and throughput. Now, likewise, and even more interesting, is we can run data parallel operations or computations so that we can analyze groups of data. Remember, we talked about in this earlier slide that we're storing data in collections by type. For example, cars or wind turbines or shoppers. So by using this technique of organizing objects in collections, we can run a method we call a val, or an evaluation method, on all of the objects in a collection, and this will run in parallel on all grid workers. And these grid workers will access all of the local objects within that collection and in parallel analyze that data, and then it can optionally merge the results down to a single object which is returned to the client. So this is how we can easily run a highly scalable data parallel computation. And in the last example today, you'll see that in use for stream processing. So here's an example of a data parallel execution model just to sort of ground that idea a little bit. So you can take objects stored in the grid and run a user-defined method generally on the type of that object, which is evaluating data within that object and generating results. So you now have, for each execution and each object, you have a set of results. And these results can be merged, again, with a user-defined method, which is in this case doing a binary combining of two results, and this can be done successively on all of the results and in a distributed way to run in logarithmic time across all servers to produce a single result which is then returned to the client. And the code to do all of this can be described as one API call to ScaleOut Stream Server. So it's a very compact notation that allows us to implement this relatively complex data parallel orchestration of user-defined code. Now, an example you probably are more familiar with is MapReduce. And just to talk about that for a second, MapReduce elaborates on the basic algorithm by taking sets of objects in the grid, typically in one collection again, and extracting information from each object and then combining it locally and then partitioning it into one of a set of buckets, which are then analyzed in parallel in a second phase, which is called the reduce phase, to produce a final set of objects which represent the results. And so you may have heard of a group by operation in, or a pivot table in Excel, and these are all the same operation. So here's an example here. Determine the average RPM for all wind turbines by region, say 4 regions. So to execute this, you would take the state information for all the wind turbines that you are tracking, extract the RPM, that's part of what the map operation would do, and then map that to one of the 4 regions based on knowing the region of that wind turbine, and then forward that information to one of, in this case, 4 partitions. This shows 8, but it could be 4. And those 4 partitions then compute the average RPM for all the wind turbines in that region. Notice that these data can come from multiple servers into a given partition, and then reduce all that into 4 results, which is the average RPM for each region. And so that's what MapReduce does. So moving forward, let's now talk about stream processing, now that we have looked at all of the basic tools that we need to implement stream processing and data parallel analytics. So some of the challenges or the goals for stream processing, which have been around for many years, are to process data streams, events coming from data streams or commands to devices from thousands of sources, and to analyze these events for patterns of interest and provide either feedback to the data sources or alerts to humans. And also, a nice goal is to look at aggregate behavior across all of the data sources to see what aggregate statistics can be extracted and used to feedback and improve the operation of the live system. That's what we call operational intelligence. So as you can imagine, there are many applications, and I don't need to elaborate all of these applications. As the audience here, you probably know more about some of these than I do, but just to give you an example, we'll look at e-commerce recommendations. And the question really is, when we're performing these functions for stream processing, how do we track the dynamic state of data sources to enhance the analysis? This is a topic that has not been generally addressed by the stream processing community, and yet it's extremely important to do a good job of stream processing. So let's take a look at this example of e-commerce recommendations. So imagine a large website with thousands or hundreds of thousands of shoppers, especially during the holiday season where shoppers are looking for presents and so forth. What we want to do with a recommendation system is watch the click stream of clicks that a shopper is performing to look at products and decide which product in a given category to buy, and then to make immediate recommendations to assist that shopper in finding the right product or the product that the merchandiser wants to push to that shopper. So there's sometimes conflicting goals, but the net result is we need to make recommendations back to the shopper in under 100 milliseconds. So the shopper can take that into account and help steer and the shopping process, make it more efficient and more enjoyable. Now, to do a really good job, this analysis should be taking into account the shopper's preferences and demographics. So information about each shopper, not just looking at the click stream. So this is a case where we want context information about the shopper, not just data about the click stream. And we also would like to look at what all the shoppers are doing that are shopping in a given category, so we can provide aggregate feedback to that shopper to assist the shopper in knowing what's popular, what's selling the best. So this is an example here of a UI that one could construct. We constructed as a demonstration of real-time stateful stream processing for e-commerce recommendations. And what it's doing is, as shoppers click on products, we create a frame on the web page which is showing various products that we are recommending based on their clickstream history, and also based on our knowledge of their past shopping behavior, their favorite products, the favorite brands, for example, the price range they seem to operate in, low, medium, high, and also any other data about their demographics that's relevant to the shopping experience. So as you might imagine, their location, so if they're in the north, heavier coats, and if they're in Florida, lighter coats, and that sort of thing. So knowledge of the data source allows us to do a better job of making these recommendations. Now, we also can feed back to them aggregate statistics of what are the best-selling, the most viewed products. This is an example of feeding back real-time aggregate statistics gathered using data parallel computing. In addition, we can let the shoppers tell us about their preferred brands and features for a given product, and we can track that as they click through various products and help refine our recommendations. Now, the aggregate statistics can also be displayed for the merchandiser in a chart like this, helping the merchandiser see what are the most popular brands, the most popular products within a category, and so forth. And that allows the merchandiser to create real-time promotions or to steer pricing and so forth. In addition, it allows us to have collaborative feedback that we feed back that we just saw to the shoppers. So this is an example of stream processing that's addressing these challenges that we saw here of how to track the dynamic state of data sources to enhance real-time analysis. So the question is, how do you implement it? How do you track the state of data sources? If you look at a typical stream processing pipeline right here, which you will see when you look at Apama, Flink, Beam, Storm, many different stream processing systems, the task of tracking the state of data sources is usually left to unmanaged data storage outside of the pipeline, and it's usually an assignment to the developer to go cobble together a storage mechanism and then to access it during the stream processing, within the stream processing pipeline. And the problem with this, there are several problems with this approach. First of all, it's not integrating context information into the pipeline. There's no standard repository that's integrated into the stream processing model by which events can be associated with context quickly so that they can be analyzed in the context of the knowledge of the data source. So that's the first problem. The second problem is this is adding complexity because every developer has to address this problem individually, and this also creates a network bottleneck as each of these pipeline stages here has to go access secondary storage outside of the pipeline, which typically requires a network transfer. And we'll see in a few minutes how that can really kill performance. Lastly, it doesn't even talk about data parallel analytics and how can we get aggregate statistics to feed back. Typically, this is done with the Lambda architecture, which is feeding that forward into a system like Spark for analysis offline through batch processing and presentation to users. I'm going to go to a slide that's much later in this presentation just to show you what I'm talking about here, if I can find it. Yeah, here it is. So if you look at, so this jumps ahead a little bit, but if you look at the Lambda architecture, this is the typical way this problem is tackled of providing aggregate statistics through data parallel analysis. The speed layer and the batch layer are separated. Events can come into both, but when they go into the batch layer, they're just stored for offline processing, as I say, typically with Spark. And if you look at just one example of that, this is the Azure IoT Services architecture. You see there's an IoT hub here which is receiving events from devices and then forwarding them to streaming analytics, which again is pushing them into storage and processing them offline for presentation typically to humans. So what you really want to do is do this data parallel processing live in real time, provide real-time feedback, not just feed it forward to users, to analysts for offline processing and analysis, but to feed it back into the live system with very low latency so that you can steer behavior in real time and improve the efficiency of a system. And we saw that in this example of e-commerce recommendations, because if you can perform data parallel analytics in real time within seconds, then a shopper can see what's selling, this hour, this minute, right now. So if they're looking at refrigerators, what's the hot product or what's the most viewed product, and that helps them to refine their search. So it's extremely valuable to have data parallel analytics processed live in real time. So how do you address this challenge of efficiently combining stream processing with state information or context to enable real-time analytics and also to allow data parallel analysis for aggregate behavior, and at the same time keep the design simple and have very high performance? So the answer, or an answer, I'm sure there'll be other answers down the road, is to leverage what's called the digital twin model. And when we first saw this model a few years ago, we recognized that it came from a different environment. In particular, it's a field called product lifecycle management, which many of you might, who are listening here, might actually be in that field and not in stream processing, and that's something that we like to learn. However, we're applying this concept to stream processing in real time, not just to feedback to product lifecycle management, real-time telemetry so that product manufacturing and design can be improved, but to allow a live stream processing system to process events and provide feedback to that live system so that it can operate more efficiently and more effectively and more cost effectively. So if we look at this term was recently popularized in 2017 and then again this year by Gartner as a strategic trend for IoT. And so we think that this concept will migrate into stream processing and not simply be confined to product lifecycle management. But there is some confusion there, and I'll go into that in the next slide. For now, let's just talk about the Gartner definition. At a high level, a digital twin is a model, typically of a physical data source or physical structure, which can be a substructure in a more complex system. And it has associated with it data for that instance, I like to say in an object-oriented term, that instance of the physical structure. Of course, it has unique identity, And then it has this notion of being monitored for alerting. So code can run that makes use of both telemetry and data associated with that data source. So what's significant here is that the digital twin model shifts the focus from the event stream to the data sources. If you look at typical stream processing, it's looking at the event stream. So the event stream is the center point of the software architecture and the design. And notice you have data streaming from many data sources, but the data sources are not first-class citizens in the stream processing pipeline. Tracking data sources must be done by the application explicitly. Whereas in the digital twin model, the data sources become first-class citizens, and the events or telemetry becomes an artifact of the data source which can be analyzed. And by doing this, we provide a deeper context for introspection and interaction with the physical data source. It allows us to do things that would be otherwise much more difficult in our application code for stream processing. So let's look at how this term is used and how it's migrating into stream processing. So as I mentioned, it's typically used for product lifecycle management. Interestingly, and so there's some articles by Mark Lin that talk about that. Now, interestingly, Microsoft Azure now talks about, as of this year, digital twins. But again, they're using them more in the context of product lifecycle management, describing a graph of spaces, devices, and people, so that you can, for example, model a huge office building and know which chairs are in which rooms, and what are the what resources are available at various floors and that sort of thing. So it's lifecycle management for buildings, if you will, or other spaces. It's as opposed to for stream processing per se. So it's not integrated into their stream processing architecture. However, as we go into Azure and AWS device twins, they are a closer representation of a digital twin, except they are they represent a very restricted amount of state information that's has evolved from the IoT community that's tracking the desired state and the reported state of a given physical device. And so it's not really thought of as an object-oriented construct which can have real-time analytics integrated into it. It's designed as a repository for per device, per source state information, so that they can be conveniently accessed. For example, if you're tracking all the light bulbs, smart light bulbs in an office building, and you want to know are they on or off, then you can have device shadows in AWS which can do that and send a message when the state of a light bulb changes. Again, it's a narrow use of the digital twin concept just for tracking the simplified set of state, typically in Azure, for example, no more than about 50 kilobytes of state of an IoT device. So our use of this term, digital twin, elaborates on that to provide a fully featured object-oriented model of the data source for performing real-time streaming analytics. And the benefits of doing this is that it's integrating real-time streaming analytics, both handling events and doing data parallel analysis on those digital twins to provide feedback to a live system that's very easy to implement, very easy to use, highly scalable, and allows for much deeper introspection than otherwise. So we're bridging the gap between the simple device twin, device shadow, and real-time analytics so that we can turn the Lambda architecture upside down and do this in real time. No more need for batch processing to do analytics in real time. Although, of course, offline batch processing will always be valuable for looking for patterns and trends that aren't relevant to real-time feedback. So here are just some examples, pictures that show you, devices or systems with devices that can be providing telemetry streams and receiving feedback from digital twin models. And we'll go look at this in some detail. So the next step is to look at what is a digital twin model in the concept we're talking about here. So it's an object-oriented view of the state of a data source and the code which analyzes events and performs data parallel analysis. So there's a model which is an object-oriented type, and it corresponds, for example, to say a wind turbine. So one would define a model for a wind turbine or for a valve or for a controller or a generator, and then one would create an instance of this model for each physical data source that we want to receive telemetry from or command. So if we look at it here, this object has inside of it an event collection. That's if the implementer decides they want to track events, and we'll look at some examples of that. It's not necessary to track every incoming event, but that may be desired. One might also just track incidents or interesting events, a filtered set of events, which are of interest for analysis, and thereby conserve memory so it doesn't grow exponentially, as every device source generates events. Likewise, it incorporates state. This is the key. The center point of the whole object is dynamically evolving state information about that data source. So if we're looking at an e-commerce shopper, this might be the preferred brands. If it's a wind turbine, it might be how much time is left before the next maintenance period. Has this wind turbine ever oversped? That kind of information. Knowledge that helps us to interpret and analyze incoming events. So as events come in, they can draw upon the digital twin state, and also they can look at the event collection, which can be analyzed using time windowing techniques. And I might add, we have time windowing libraries available in C#, Java, and JavaScript. Doing time windowing with digital twins is completely straightforward. It does not require an Apache Beam style pipeline to do time windowing. But that's a subject of another talk. So this digital twin encapsulates not only state, but also code, user-defined code for analyzing events, for perhaps posting and evicting them from event collections, and the time windowing library would perform this function here. But also user-defined code that understands, for example, what a wind turbine is and what it means to have received a given event in a given state, and what alerts we need to generate or feedback we need to generate. Now, in addition, very interestingly, digital twins can accept commands, and commands can then be forwarded as feedback to physical devices to change their state. So another use of digital twins is an intermediary that accepts high-level commands and performs the detailed actions needed to change the state of a data source according to the need of that command. So the object-oriented model has several advantages. First of all, we saw that it's encapsulating both state and code using standard object-oriented techniques. There's no new language here, as you might see with Apama. It's using standard techniques. The other advantage is it can incorporate and encapsulate other types of analysis algorithms, such as a rules engine or an incrementally learning machine learning algorithm, so that this code can be just encapsulated in an object-oriented manner and orchestrated by the grid independently of the application. That's an important concept which we won't talk about a lot, but what's important is the specifics of an application and perhaps the proprietary nature of that application can be encapsulated and managed, that is to say orchestrated, run on the grid, deployed to the grid without any integration with that application. So unlike other stream processing architectures which require the use of certain APIs to implement the stream processing, these two are cleanly separated using object-oriented techniques when run as digital twins. That's another benefit of the digital twin model. And lastly, data can be extracted for data parallel analytics. We'll see an example of that. In addition, data can be pushed out to offline if it's not accessed frequently, or pulled in from offline if it's needed. So, for example, in fraud detection, if you start seeing a set of events for a given wire transfer customer that start to look like fraud, you could start pulling in offline state to learn more about who that customer is and have they had problems in the past and so forth. So offline state can be integrated easily with the digital twin model. So why host them on in-memory data grids? Well, first of all, let's look at this as, what are we doing with a digital twin model on an in-memory data grid? Well, we're hosting them as objects, and we're posting events to them that are, as I mentioned earlier, when an event comes in, it can be forwarded to a specific object in the grid to execute the user-defined code. That's exactly what we do to run the event handler. So the event handler runs on the server on which the corresponding digital twin object exists. So if we go back to this chart we looked at before of doing event processing, so the event is sent to a particular host where the specific digital twin object lives, and then it's run in the IG worker, and that event handler is run as user-defined code, which has been shipped out previously to the model has been shipped out to the grid worker, and then the state information is accessed immediately from the local server, so there's no network transfer required to run the digital twin model, process, and event. Secondarily, we can extract data for data parallel analysis using the techniques of the in-memory data grid we looked at before, because the collection of digital twins, say all the wind turbines, can be accessed as a group and analyzed in parallel, and this feedback can then be given back to their event handling algorithms to steer their behavior, as we saw with the e-commerce application, and we'll see in another example. So what are some of the advantages of this approach? The key advantage is because in-memory data grids implement object-oriented data storage, this is a very natural repository or hosting environment for digital twins. There's no need for us to create more infrastructure. In fact, that's why we identify digital twins as a very useful higher-level structure or software architecture for organizing stream processing, because not only does it allow deep introspection by giving immediate access to state information, but it's very naturally hosted on an in-memory data grid, and the event handling and data parallel computing are very naturally performed within an in-memory data grid to give us scalable throughput and integrated high availability. In addition, as I mentioned, it provides for clean separation of the application code from our data parallel and event handling orchestration, in addition to allowing the user to incorporate specialized algorithms in a very clean, well-understood, object-oriented manner. And the net result is very high performance without network bottlenecks, unlike a traditional stream processing pipeline, and integrated high availability. So if we compare that to a traditional architecture, what we're doing is we're automatically correlating the events from a given data source. Instead of leaving that to the application, they're automatically correlated and sent to a code defined by the user that's associated with context information about the data source. Another more subtle thing is that instead of constructing the stream processing algorithms as a pipeline in stages, as you might with Storm, for example, the code is all organized in one place inside of the digital twin model, the object-oriented definition. And that makes for a simpler way to conceive this code and to store this code for execution. You're avoiding shipping data across pipeline stages to get it to the next stage in the pipeline. This is naturally done automatically using the multi-core, multi-server architecture of the grid. And lastly, of course, the data parallel analytics. Now, just to look for a second at the network bottlenecks. So with stream processing pipelines, we looked at this bottleneck that can occur, and you can see what the effect is here. This is an example that we performed on our grid where we were not accessing local data, but instead going randomly across the network to access objects in the grid. And because networks are the bottleneck in modern computing systems, not memory, not CPU, it's the network today, because we're still at 1 gigabit, even though CPU cores, counts, and speeds and so forth have increased dramatically, as is available memory on each server. So the network is the bottleneck, and you need to have applications stay off the network as much as possible, or the throughput does not scale as the workload increases. So this is a graph of throughput scaling, and you can see the effect of a network bottleneck. So there are many applications for this digital twin model, and you can imagine how they might be used, for example, for IoT devices to analyze and do predictive analytics. For example, marine engines, generators, wind turbines, the list goes on. Medical monitoring is a particularly useful use of the digital twin because knowledge of a patient's history and medications and condition procedures really helps in analyzing various telemetry that are being delivered to the digital twin, so that more refined alerts can be provided than if this information is not factored in. And we worked with SUNY and for a period of time in looking at the benefit of this, and medical people say that that in the ICU you can get much better analysis if you have this information than if you just look at the immediate telemetry, which is what most doctors and nurses are forced to do in an ICU. Just look at what the charts are telling them at that moment. Cable TV is another example. It's very much like e-commerce in that you're looking at viewer behavior and trying to either make recommendations or look for set-top box failures or look for network bottlenecks if a big sporting event is occurring. Many things you can do with digital twin models when you have knowledge of the viewer and knowledge of the set-top box, and when you get telemetry in a cable system. This is another example that we looked at in some detail along with e-commerce. And I talked about fraud detection. There are many other examples such as security systems and credit card transactions and so forth. Here's an example just to sort of drive the point home a little bit. If you're tracking a fleet of vehicles, maybe they're rental cars, maybe they're trucks, you can get telemetry from these vehicles, and with your knowledge of the vehicle and its driver, you can make better, more informed decisions about what feedback to provide. So, for example, if it's a rental car and what you're finding is that the driver is under 30 and speeding, that might be different than if the driver is between 30 and 50. It's your algorithm for providing feedback. So you could help detect lost vehicles if you know something about what the constraints are and what states the vehicle is supposed to be in. So knowledge of the data source and being able to access that in real time and provide immediate feedback allows you to do a better job of processing the incoming telemetry. And also, as you can see here, it allows you to do a better job of looking at aggregate behavior of all of the data sources together. So, for example, you can optimize fuel efficiency for trucks if you can do data parallel analysis, MapReduce on statistics about a fleet of trucks in real time and not offline. So we're bringing the optimizations home in real time to steer the live system. Now, object-oriented techniques give us a lot of leverage points, which I won't dwell on in this talk since we're running a little bit long here. I want to get to the examples, but here are some examples of what you can do. You can use inheritance in object-oriented programming to make subclasses of digital twin models. So here's a basic controller model, and then you can make a hot water valve which has new methods defined on it and new state information defined on it. Here are the methods and the state. Likewise, you can organize digital twins in a hierarchy so that higher level twins are looking at abstract devices, if you will. So the lower level twins are looking at physical devices or talking to physical devices and then forwarding information to higher level twins looking at subsystems. So here's an example of that for a wind turbine. So you might have digital twins for various subsystems within a wind turbine, the blades, the generator, and the control panel. These are the 3 digital twin instances for this wind turbine. And they can forward statistics to higher level digital twins, which represent higher level or more abstract subsystems in the overall model. This, for example, looking at the blade system as a whole. And then this one looking at the wind turbine as a whole and looking at not only the tower components that are rotating, but the control system, and looking at alerts and combining them with intelligence at a higher level, much as our nervous system does as it moves to higher levels in the nervous system, in order to process this data in a modular way with a separation of concerns from managing the physical devices to managing the various subsystems and the entire system as a whole. So hierarchy is another benefit. A third benefit is migrating to the edge. So if you look back at this one, these digital twins can be migrated to the edge. As we know, processing power at the edge is growing dramatically, and edge computing is all the rage this year and will become even more important. And the use of containers to run streaming analytics at the edge is also becoming prolific. So the digital twin model allows us to migrate functionality without reprogramming for the edge. We simply change the protocol for shipping telemetry and feedback up into the cloud for doing higher level processing. And so the successive refinement can be performed, and maybe over time the blade system would, if it can be, would be moved to the edge. And so we can think about using digital twins as a basis for partitioning logic between the edge and the cloud in stream processing. And lastly, for data parallel analytics. So if you have a set of digital twins, you can use these techniques like MapReduce to extract information out of the state of the digital twins and either report it or feed it back into the digital twins. And we'll see an example of that in just a minute. So we have constructed what we call the ScaleOut Digital Twin Builder Toolkit. And this toolkit allows developers to construct digital twin models in Java or C# and JavaScript is coming in our next release, and then deploy those models directly to the grid for processing. What we're doing is eliminating the need to program directly to the lower level APIs of ScaleOut Stream Server. So the developer stays focused strictly on the digital twin model, defines a digital twin or set of digital twins, deploys them out to the grid with one API call, and then receives telemetry from various data sources. We've built connectors to Azure, Kafka, and we have a REST messaging service, and we are about to roll out our AWS support. And then this will automatically ship these events into the grid and to their respective digital twins for event processing. So the idea here is to minimize the API footprint of our in-memory data grid so that applications can be constructed strictly using the digital twin model. So let's look at an example of that in C#. And to give you a flavor of the power of the digital twin model in analyzing the state of a physical system by making use of information about the data source. So this application is looking at temperature telemetry from wind turbines. This is a picture I took this summer at Block Island. You may be aware there's a wind farm there with there's 3 of the 4 wind turbines that's just slightly offshore, generating a huge amount of power. And a very successful experiment in the Northeast. So we just constructed a hypothetical model of the wind turbine, trying to differentiate what high temperature readings mean and how they should be handled given on whether a wind turbine is in a pre-maintenance period or not. So that's an example of context about a given instance of a wind turbine. So as we get over temp readings from the wind turbine, we want to handle them differently if they're in normal operation or in pre-maintenance, in which we might want to step in more quickly and shut down the wind turbine. So our message processing is looking at for onset of an over temp condition and alerting when a maximum allowed duration occurs. And it's using this time windowing concept to analyze events that have been logged. So let's just look at the code. So we're going to look at code for the next several slides, and I'll try to make it as brief as possible. So this would be how one defines the state object for a digital twin model, in this case of a wind turbine model. So we define a base class, and users can implement that base class to construct a wind turbine state object, which has various properties associated with it. So we're tracking, in this case, the model, the next maintenance state that's for this, and dynamic state, other parameters, and then the dynamic state variables, such as are we now tracking an overtemp condition? When did it start? And how many messages have come in reporting overtemp? In addition, we can keep lists of incidents, or we could keep all the incoming temperature events if we wanted. This just shows keeping an incident list so that we can go back with time windowing and see, what was the pattern of incidents that has occurred. So the code that's processed, so the user defines 2 things, this state object, and in addition, a message processing method. And this message processing method takes an instance of this is an instance of that state object, and a list of messages that have come in. Most of these IoT platforms will deliver messages in groups, and that allows us to maximize throughput and minimize overall latency for handling those messages. So we want to be able to handle a group of messages at one time. There's also this thing called a processing context, but we can ignore that. That simply provides us with additional information we might want to make use of for tracking the behavior of the data source. So what this algorithm here is, we won't go through in detail, but I think you can read it and see what's going on. We first want to determine if, based on the model of wind turbine we have, are we right now in a pre-maintenance period? Yes or no? And so we'll determine that, and then we'll know what time it started. So I'm sorry, what time the overtemp, if an overtemp occurs, what time it started. So we're going to look at these messages, and if we see an overtemp situation, we'll track it. If we see we're not in an overtemp, we'll resolve the state. And the next slide shows you these two subpieces here. So if we're tracking an overtemp condition, if we're not tracking it, we start tracking it if an overtemp message has come in. And then we look and see what its duration is. And here is where we're refining our behavior based on our knowledge of the data source. In this case, is this particular wind turbine due for maintenance? And if so, are we within the pre-maintenance period that this alert has occurred? And if so, that's what this if statement is about, then we send an alert. And otherwise, we don't, because we're not in a pre-maintenance period. So this is just a very, very trivial example of how you can track the dynamic state of a data source and change the behavior of your event handling code based on that knowledge. This state would have to be held in an ad hoc manner with a traditional stream processing platform. There's no place to hold these state variables, or for that matter, to host this information. And furthermore, the incoming events would not be automatically associated with this state. This is what the grid is doing for us. It's co-locating the messages and the state information. So with extremely low latency, we can access it and process these events right here in the context of that state and make these decisions. And this shows just simply resolving the overtemp state. So that's the benefit of the digital twin model and how it can be simply defined. Now it also can be deployed with, as I mentioned, one API call where you simply create a new execution environment for that model, tell us where the DLL is, and give us the name of the method that you're using to process messages. And so with this very simple program statement, you can deploy the entire model to the grid, and the code will be shipped out to the grid and ready to process events. And then you can, with another program statement, for example, connect to Azure IoT Hub, and messages will then be streamed in a highly parallel, scalable manner from Azure IoT Hub into the grid and sent to instances of digital twins. Now, digital twin instances are created on the fly as messages come in, and these and instances do not exist for the associated data source. So we're just deploying the model. The instances get created as needed when the messages come in. So let's look at a second and final example before we wrap up. This is heart rate watch monitoring, and this gives you more information about how one might incorporate data parallel feedback into this model. So what we're doing here is tracking telemetry from exercisers, people who are exercising with heart rate watches, and then looking at aggregate behavior of all of the people exercising, and looking at the dynamic parameters and state of each person to see, what are their medical conditions and so forth that would require us to send alerts to them in addition to the aggregate results. So let's dive into that a little bit. So this is in Java, and this represents the state object for a given user who's exercising with a heart rate watch. And notice it's tracking various things like body weight, gender, average heart rate. You can read all this. What's interesting here is the medication. So if we know what medications they're taking and what heart rate incidents they've previously had and medical conditions, we can now make a better decision of analyzing a list of heart rate telemetry that's being accumulated from the watch. And we can then provide more effective feedback. So a heart rate event is just another Java class, and an alert is another Java class. This is just to show you that they're very easy to define and implemented as serializable JSON objects. And then this is the heart of it, no pun intended actually, to processing a message for a user that's receiving a heart rate event or a collection of those, a set of those, coming in to this state object. So here again is the digital twin state object, and here are the incoming messages. And so what we're going to do is we're going to, first of all, track these incoming heart rate events in a set of session windows. So we're using one of the three techniques we support for windowing, for doing time windows, session windows, because typically people exercise in sessions, and this time windowing library automatically will add in a time-ordered fashion a new heart rate event and also perform the necessary eviction for unwanted heart rate events based on the policy we set when we define the window. What's interesting is these windows are defined as enumerables, so that they can be very efficiently handled by the application without slinging arrays back and forth. We only pull the data we need when we need it. So for example, down here, we're going to look at each of the windows and compute the average heart rate in those windows, and then the overall average heart rate for the user across a set of windows that we're tracking. Just to give you an example of how time windowing can be used to track incoming telemetry, as you might do in a standard stream processing system. But here is where we just feed this into much deeper analysis of the heart rate event. We have this information now. We're setting the average heart rate. That's interesting. But now we can look beyond that and look at the details of that particular user to see what we want to do. Now, I'm not going to describe code here because it would be too lengthy, but this gives you an idea of some of the monitoring and feedback we can perform with the digital twin model. We can look at the type of exercise they're performing and give them feedback. We can look at their particular history and medical events to provide alerting. We also can look to see whether they should be changing the exercise they're doing because they're doing one exercise too frequently, or their sessions are too long, or they've certain exercises are creating peak heart rates that are too high. We also can generate aggregate statistics such as the average heart rate and average BMI for all users in a given age range, and feed that back in to notify them if they deviate significantly from aggregate statistics. So these are some of the examples of what you can do with a digital twin model in analyzing telemetry for users of a heart rate watch, and in general for tracking people based on their medical condition and their activity. So let's look at how one would implement this data parallel computation to show you how simple it is to take this digital twin model, extract this information, and then feed it back into the model. So this will go kind of fast, but it's it shows how simple this actually is. So as I mentioned very early in the talk, you can create an eval method and a merge method. These are defined by the user, and they're simply going to call an underlying helper method defined by the user, which we'll look at in the next slide, called merge, which will serve to work for both creating extracting statistics from the digital twin and for merging those statistics across multiple users. So when you define this by implementing this interface called invocable in Java, then this code can be shipped out to the grid for execution. And this is separate from the digital twin model, but it's reaching into the collection of digital twins of the users in this case to extract this information. Let's see how that's done. So what happens is when we run the eval method or the merge method, it's going to call this helper method called merge, which is going to go into a user object and extract information out and then accumulate it and return this information. So it's looking at here heart rate, count, and also there's BMI. So it's extracting information out of these digital twin objects and also organizing them into groups in a MapReduce style computation performed without formal MapReduce semantics. And then the next step is it's going to combine that and return that. This is used both for extracting data and for merging it in this. I'll just go back to this algorithm to show you. So it's being used both to do the extract data out of the digital twin objects and to do a binary merge for two sets of results, and then perform that successively to generate one result object with this extracted and averaged information. So if I can find my way back to where I was, which might take a second. Let's see, where was I? Yep. Okay. So. Here we are. So we're extracting and accumulating heart rate information, the count of that, and BMI information and the count of that. And this can then be merged with the merge algorithm and then delivered back to the user. So to execute this data parallel algorithm, we only need to run one statement, which will invoke that data parallel execution, run it, and return a result in this result object, which we then can perform the final averages, taking the sums and the counts and performing the final average, and leave that in an object which we can then put in the grid for access by the digital twin. So this analysis algorithm can then access the latest global statistics, which can be computed every few seconds using data parallel computation, extracting data from the digital twins. So to wrap up, um, we're seeing here how digital twins can provide a next generation set of capabilities for stream processing because they're addressing the challenges that we saw for stateful stream processing, namely the lack of a context or a data store for managing context and an efficient way to manage that context so that we avoid network bottlenecks. And the digital twin model is a flexible, very intuitive model for processing events and doing aggregate analysis, as we just saw. And stateful stream processing with digital twin models allows us to integrate stream processing and real-time analytics in one coherent, unified model, which has clean separation of user-defined code from our platform and allows users to have deeper introspection than previously possible. So if you'd like to learn more, please check out our website. And we have a user's guide for the digital twin builder there, which here's another link, and we'll send the deck out to anybody who's interested. Also, we have a blog which has several articles about digital twin models and their power and usefulness. In addition, you can take a look at the Java and .NET and REST digital twin libraries to help you build applications with ScaleOut Stream Server, and we'll be adding another for JavaScript in our next release. So thank you very much for attending, and I meant to end early, but at least I ended on time. So if there are any questions, I hope you forwarded them to Dave Brinker, and we'll see if Dave has any questions.
Well, thank you very much for that, Bill. There are a couple of questions that have come in. We're sort of at the top of the hour, but maybe we have time to do a quick answer on one or two of these. The first one is, how does machine learning and AI fit in with the use of digital twin modeling?
Well, machine learning models and AI can be incorporated into the analysis code within a digital twin. So the nice thing about the model is that it allows the user to incorporate a rules engine or machine learning algorithm into the digital twin model to be deployed for execution with all digital twin instances. Now, typically, these machine learning models are trained offline on, say, in the cloud in a large machine learning training environment. For example, on Azure, I was at a conference last week in which Microsoft demonstrated how you could train a model and then download that model for execution for individual data sources. So this model would be trained, downloaded into this object, and then used to process incoming events based on a trained model. Now, long term, we really want to have these models train themselves or incrementally improve their behavior without having to go through a batch processing training phase. But the current technology, that's too ambitious for execution within digital twins. But as far as I know, in any case, that's where it fits in. What we're providing with the digital twin model is an infrastructure for executing various analytics algorithms that process incoming events and commands, and a machine learning algorithm is just one of those. A rules engine could be another, and a simple C# or Java code could be a third. I hope that answers the question. Do you have another, Dave?
Okay. Well, there's a related question possibly to that. Could a single digital twin model be used for multiple purposes, specifically both for PLM, product lifecycle management, as well as streaming real-time analytics?
Well, I could see that being done, although I do think that it's more of a management issue than it is a technical issue. Typically, people that are concerned with product lifecycle management would not be concerned with day-to-day management of a live system, to my knowledge. But perhaps in the future, people would create digital twin models for use in lifecycle management and then make those available along with the devices as a management tool for use in the field and providing immediate feedback, in addition to sending telemetry back to the factory for improving the behavior. Much as a Tesla car has intelligence to both provide feedback to the driver and send feedback back to Tesla to improve, for example, the lane keeping and that sort of thing. And that sort of thing could be done with digital twin models as well. So it's more of a management issue than it is an object-oriented design issue. And it's important to understand the typical challenges that you have with object-oriented programming exist with digital twins implemented using this technique. So in particular, if you have a large programming team, you need to have standards and techniques by which digital twins are constructed in a consistent manner across many device types, and able to be formed into hierarchies and so forth. So it's the standard object-oriented challenges, but with all the benefits that you get from object-oriented programming. Go ahead, Dave.
Okay. Maybe just one more. This is my personal favorite. How do I download and test ScaleOut Stream Server? And does ScaleOut provide technical assistance during a pilot project?
Well, that's a question you should answer.
I
but
could answer that.
I'll
Go
start
ahead.
it out with going to this slide. Go to scaleoutsoftware.com, and I'll turn it over to Dave to finish that.
Yes, you just click the Try for Free link on any page on the site, and you can download whichever product you want. And the answer is yes, we do provide technical assistance during a pilot project. You can just email support@scaleoutsoftware.com. I think that's probably it. Bill, thank you very much.
Thank you all for attending.
Presentation.
Yes, thank you. Thank you, Dave, and thank you everybody who attended. And we'd be very interested to get your feedback and help you move forward with using digital twin models. So have a great rest of your day, and thank you.